Last time, Tuesday, we discussed Boxplot, and we introduced how can we use Boxplot to determine if any point is suspected to be an outlier.
Yes.
And by using the lower limit and upper limit. And we mentioned last time that if any point is below the lower limit or is above the upper limit, that point is considered to be an outlier. So that's one of the usage of Boxplot. For this specific example, we mentioned last time 27 is an outlier. And also here, you can tell also the data are right skewed because the right tail exactly is much longer than the left tail. The distance between or from the median and the maximum value is bigger or larger than the distance from the median to the smallest value. That means the data is not symmetric, it's quite skewed to the right. In this case, you cannot use the mean or the range as the measure of spread and median, and mean as the measure of tendency, because these measures are affected by outliers. In this case, you have to use the median instead of the mean and IQR instead of the range, because IQR is the mid-spread of the data, because we just take the range from Q3 to Q1. That means we ignore the data below Q1 and data after Q3. That means IQR is not affected by outlier, and it's better to use it instead of R, of the range. If the data has an outlier, it's better just to make a star or circle for the Boxplot, because this one mentioned that that point is an outlier. Sometimes outlier is maximum value or the largest value you have. Sometimes maybe the minimum value. So it depends on the data. For this example, 27, which was the maximum, is an outlier. But 0 is not outlier in this case, because 0 is above the lower limit. Let's move to the next topic, which talks about covariance and correlation. Later, we'll talk in more details about correlation and regression. That's when maybe in chapter 11 or 12. But here we just show how can we compute the covariance or the correlation coefficient and what's the meaning of that value we'll have. The covariance means it measures the strength of the linear relationship between two numerical variables. That means if the data set is numeric, if both variables are numeric, in this case we can use the covariance to measure the strength of the linear association or relationship between two numerical variables. Now the formula is used to compute the covariance is given by this one. It's summation of the product of xi minus x bar, yi minus y bar, divided by n minus 1. So we need first to compute the means of x and y, then find x minus x bar times y minus y bar, then sum all of these values, then divide by n minus 1. That will give the covariance. The covariance only concerned with the strength of the relationship. By using the sign of the covariance, you can tell if there exists positive or negative relationship between the two variables. For example, if covariance between x and y is positive, and that means x and y move in the same direction. It means that if x goes up, y will go in the same position. If x goes down, also y goes down. For example, suppose we are interested in the relationship between consumption and income. We know that if income increases, if income goes up, if your salary goes up, that means
Consumption
the assumption also, the consumption also will go up. So that means they go in the same or move in the same position. So for sure, the covariance between x and y should be positive. On the other hand, if the covariance between x and y is negative, that means x goes up, y will go to the opposite direction. I mean, they move to opposite direction. That means there exists negative relationship between x and y. For example, your score in statistics and number of missing classes. If you miss more classes, it means your score will go down. So as x increases, y will go down. So there is positive relationship or negative relationship between x and y. I mean, x goes up, the other go in the same direction. Sometimes there exists no relationship between x and y. In that case, covariance between x and y equals 0. For example, your score in statistics and your weight. It makes sense that there is no relationship between your weight and your score. So in this case, we are saying x and y are independent. I mean, they are uncorrelated. Because as one variable increases, the other maybe go up or go down, or maybe constant. So that means there exists no relationship between the two variables. In that case, the covariance between x and y equals 0. Now, by using the covariance, you can determine the direction of the relationship. I mean, you can just figure out if the relation is positive or negative. But you cannot tell exactly the strength of the relationship. I mean, you cannot tell if there exists strong, moderate, or weak relationship. Just you can tell there exists positive or negative, or maybe the relationship does not exist. But you cannot tell the exact strength of the relationship by using the value of the covariance. I mean, the size of the covariance does not tell anything about the strength. So, generally speaking, covariance between x and y measures the strength of two numerical variables, and you only tell if there exists positive or negative relationship, but you cannot tell anything about the strength of the relationship. Any questions? So let me ask you, just to summarize what I said so far. Just give me the summary or conclusion of the covariance.
The value of the covariance determines if the relationship between the variables are positive or negative, or there is no relationship. That when the covariance is more than 0, the meaning that it's positive, the relationship is positive, and when one variable go up, the other go up, and vice versa. And when the covariance is less than 0, there is a negative relationship, and the meaning that when one variable go up, the other goes down, and vice versa. And when the covariance equals 0, there is no relationship between the variables.
And what's about the
It's not telling about the strength of the relationship between them.
So just tell the direction, not the strength of the relationship. Now, in order to determine both the direction and the strength, we can use the coefficient of correlation. The coefficient of correlation measures the relative strength of the linear relationship between two numerical variables. The simplest formula that can be used to compute the correlation coefficient is given by this one. Maybe this is the easiest formula you can use. I mean, it's a shortcut formula for computation. There are many other formulas to compute the correlation. This one is the easiest one. R is just sum of xy minus n is the sample size, times x bar is the sample mean, y bar is the sample mean for y, because here we have two variables. Divide by square root don't forget the square root of two quantities. One concerned for x and the other for y. The first one, sum of x squared minus nx bar squared. The other one is similar just for the other variable, sum y squared minus ny bar squared. So in order to determine the value of r, we need, suppose for example we have x and y, data x and y. X is called explanatory variable, and y is called response variable. Sometimes x is called independent, so x is independent, and y is dependent. For example, suppose we are talking about consumption and income, and we are interested in the relationship between these two variables. Now, explanatory variable or the independent, this one affects the other variable. As we mentioned, as your income increases, your consumption will go in the same direction, increases also. Income causes y, or income affects y. In this case, income is your x. Most of the time we use x for independent variable and y for independent. So in this case, the response variable or your outcome or the dependent variable is your consumption. So y is consumption, x is income. So now in order to determine the correlation coefficient, we have the data of x and y. The values of x, the number of values of x should be equal to the number of values of y. So if we have 10 observations for x, we should have the same number of observations for y. It's pairs. x1, y1, x2, y2, and so on. Now, the formula to compute r, the shortcut formula is sum of xy minus n times x bar y bar divided by square root of two quantities. The first one, sum of x squared minus nx bar. The other one, sum of y squared minus ny bar squared. So the first step we have to do is to find the mean for each x and y. So first step, compute x bar and y bar. Next, if you look here, we have x and y, x times y, so we need to compute the product of x times y. So just for example, suppose x is 10, y is 5, so x times y is 50. In addition to that, you have to compute x squared and y squared. So we have two new columns,
100.
X squared and y squared. Exactly 125. Do the same calculations for the rest of the data you have. We have other data here, so we have to compute the same for the others. Then finally, just add xy, x squared, y squared. Then plug the values you have here in this formula in order to compute the coefficient.
Now, this value ranges between -1 and +1.
so it's between -1 and +1. That means it never smaller than -1 or greater than 1. It's between -1 and +1. Makes sense? I mean, if your value is, suppose you did mistake for any of these computations, and R might be 1.15. That means there is an error. Or, for example, if R is negative 1.5, that means there is a mistake. So you have to find or to figure out what is that mistake. So that's simple calculations. Usually in the exam we will give the formula for the correlation coefficient as we mentioned before. In addition to that, we will give the summation of xy. The sum of xy is given, sum x squared and sum of y squared. Also sum of x and sum of y, in order to determine the means of x and y. For example, suppose I give sum of xi and I goes from 1 to 10 as 700, for example. We have to know that the sample size is 10, so x bar is 700 divided by 10. So it's 7. Then use the to compute the coefficient of correlation. Questions? I think straightforward. Maybe the easiest topic in this book is to compute the
coefficient of correlation or correlation coefficient. Now my question is, do you think outliers affect the correlation coefficient?
We said last time outliers affect the mean, the range, the variance. Now the question is, do outliers affect the correlation? Why? Exactly. The formula for R has X bar in it or Y bar, so it means outliers affect the correlation coefficient. So the answer is yes, because here we have X bar and Y bar. Also, there is another formula to compute R. That formula is given by covariance between X and Y. These two formulas are quite similar. I mean, by using this one, we can end with this formula. So this formula depends on Sx, Sy, standard deviations of X and Y. That means outlier will affect the correlation coefficient. So in case of outliers, R could be changed. That formula is called sample correlation coefficient. On the other hand, we have population correlation coefficient. If you remember last time, we used X bar as the sample mean and mu as population mean. Also, S square as sample variance and sigma square as population variance. Here, R is used as sample coefficient of correlation, and rho, this Greek letter pronounced as rho. Rho is used for population coefficient of correlation. There are some features of R or rho. The first one is unity free. R or rho is unity free. That means if X represents and let's assume that the correlation between X and Y equals 0.75.
Now in this case there is
no unit here. You cannot say 0.75 years or 0.75 kilograms. It's unit free. There is no unit for the correlation coefficient. The same as CV. If you remember CV, the coefficient of correlation. Also this one is unit free.
the second feature of R ranges between -1 and +1. As we mentioned, R lies between -1 and +1. Now, by using the value of R, you can determine two things. Number one, we can determine the direction and the strength. By using the sign, you can determine if there exists positive or negative. So, sign of R determine negative or positive relationship, the direction. The absolute value of R, ignore the sign.
Yes.
So the absolute value of R determines the strength. So by using the sign of R, you can determine the direction, either positive or negative.
Or no direction.
By using the absolute value, you can determine the strength. We can split the strength into two parts, either strong, moderate, or weak. So weak, moderate, and strong by using the absolute value of R. The closer to -1, if R is close to -1, the stronger the negative relationship between X and Y. For example, imagine we have this straight line. And as we mentioned, R range between -1 and +1. So if R is close to -1, this is strong relationship. Strong negative relationship. The closer to 1, the stronger the positive relationship. If R is close here,
Strong positive.
strong positive. So strong in either direction, either to the left side or to the right side. Strong negative. On the other hand, there exists strong negative relationship. So positive. So if R is close to 0,
Weak.
here we can say there exists weak relationship between X and Y. If R is close to 0.5 or -0.5, you can say there exists positive, moderate, or negative moderate relationship. So you can split or you can divide the strength of the relationship between X and Y into 3 parts. Strong, close to -1 or +1. Weak, close to 0. Moderate, close to 0.5. 0.5 is the halfway between 0 and 1. And -0.5 is also the halfway between -1 and 0. Now, for example, what's about if R equal -0.9? Suppose R1 is -0.9.
Strong negative.
Strong negative. R equal -0.8.
Strong negative.
Strong negative. Which is more strong? 9. Because this value is closer to -1 than -0.8. Even this value is greater than -0.9, but -0.9 is close to -1 than more close to -1 than -0.8. On the other hand, if R equal 0.75, that means there exists positive relationship. If R equal 0.85, also there exists positive. But
Stronger than.
R2 is stronger than R1 because 0.85 is closer to +1 than
More than.
0.75. So we can say that there exists strong relationship between X and Y, and this relationship is positive. So again, by using the sign, you can tell the direction. The absolute value can tell the strength of the relationship between X and Y. So there are 5 features of R: unity free, range is between -1 and +1. Closer to -1, it means stronger negative. Closer to +1, stronger positive. Close to 0, it means there is no relationship, or the weaker the relationship between X and Y. By using scatter plots, we can construct a scatter plot by plotting the Y values versus the X values. Y in the vertical axis and X in the horizontal axis. If we look carefully at graph number 1 and 3, we see that all the points lie on the straight line, either this way or the other way. If all the points lie on the straight line, it means there exists perfect, not even strong, it's perfect relationship, either negative or positive. So this one perfect negative, negative because X increases, Y goes down, decline. So if X is, for example, 5, maybe Y is supposed 20. If X increases to 7, maybe Y is 15. So if X increases, in this case, Y decline or decreases, it means there exists negative relationship. On the other hand, the left corner here, positive relationship because X increases, Y also goes up. And perfect because all the points lie on the straight line. So it's perfect positive, perfect negative relationship. So it's straightforward to determine if it's perfect by using scatter plot. Also by scatter plot you can tell the direction of the relationship. For the second scatter plot, it seems to be that there exists negative relationship between X and Y. This one, also there exists a relationship but positive. Which one is strong, more strong? This one is stronger because the points are close to the straight line much more than the other scatter plot. So you can say there exists negative relationship, but that one is stronger than the other one. This one is positive, but the points are scattered around the straight line. So you can tell the direction, and sometimes not all the time, you can tell the strength. Sometimes it's very clear that the relation is strong. If the points are very close to the straight line, that means the relation is strong. Now, the other one, the last one here. As X increases, Y stay at the same value. For example, if Y is 20 and X is 1, X1, Y is 20. X increases to 2, for example. Y still is 20, and so on. So that means there is no relationship between X and Y. It's a constant. Y equal a constant value. Whatever X is, Y will have constant value. So that means there is no relationship between X and Y. Let's see how can we compute the correlation between two variables. For example, suppose we have data for father's height and son's height. And we are interested to see if father's height affects his son's height. So we have data for 10 observations here. Father number one, his height is 64 inches, and you know that inch equals an inch equal 2.5 centimeters. So x is 64, son's height is 65. X 68, son's height is 67, and so on. Sometimes, if the data set is small enough, as in this example we have just 10 observations, you can tell the direction. I mean, you can say, yes, for this specific example, there exists positive relationship between x and y. But if the data set is large, it's very hard to figure out if the relation is positive or negative. So we have to find or to compute the coefficient of correlation in order to say there exists positive, negative, strong, weak, or moderate. But again, you can tell from this simple example, yes, there exists positive relationship, because just if you pick random numbers here, for example, 64 father's height, his son's height 65. If we move up here to 70 for father's height, his son's height is going to be 72. So as father height increases, also son's height increases. For example, 77 father's height, his son's height is 76. So that means there exists positive relationship. Make sense? But again, for large data, you cannot tell that. Again, by using this data, small data, you can determine just the length, the strength of a relationship or the direction of the relationship. Just pick any number at random. For example, if we pick this number, father's height 68, his son's height 70. Now suppose we pick another number that is greater than 68, then let's see what will happen. For father's height 70, his son's height increases up to 72. Similarly, 72 father's height, his son's height 75. So that means x increases, y also increases. So that means there exists both. But for sure it is hard to tell this direction if the data set is large. Because maybe you will find as x increase for 1 point, y maybe decrease for that point. So it depends on the data you have. Anyway, let's see how can we compute out. I will use Excel to show how can we do this calculations. الشاشة واضحة بس اعطوني البيانات بتاعت اكس وواي. رقم واحدة 68. 74.
75, 76, 77.
So that's the values of x. Y values
65,
70,
65, 67, 70, 72, 75, 70, 73, 76, 77, 76.
هذا equals what? So first step we have to compute x times y. So that's as x times the value of y. So 46 times 65 equals 4160 x squared. So this value squared for y squared 65 squared. And we have to do this one for the rest of the data. So that's the sum of xy, sum x squared and y squared. Now the summation, so that's the sum of x and y. Okay. We have to compute the mean of x and y. So that is this sum divided by n, when is 10 in this case. So this is the first step. Let's see how can we compute R. R, we have sum of xy minus n is 10 times x bar times y bar. This is the first quantity. The other one is square root of sum xy is sum x squared minus n x bar squared times sum y squared minus n times y bar squared. And we have to find the square root of this value. So square root, that will give this result. So now R equals this value divided by 155 and round always to 2 decimal places will give 87. So R is 87. So first step, we have x and y. Compute xy, x squared, y squared, sum of these, all of these. Then x bar, y bar, values are given. Then just use the formula you have, we'll get R to be 87. So in this case, if we just go back to the slide we have here. As we mentioned, father's height is the explanatory variable. Son's height is the response variable. And that simple calculation gives summation of xi, summation of yi, summation x squared, y squared, and sum xy. And finally, we'll get that result, 87%. Now, the sign is positive. That means there exists positive. And 0.87 is close to 1. That means there exists strong positive relationship between father's and son's height. I think the calculations is straightforward. Now, for this example, the data are given in inches. I mean, father's and son's height in inch. Suppose we want to convert from inch to centimeters, so we have to multiply by 2.5. Do you think in this case R will it change? So if we add or multiply or divide, R will not change. I mean, if we have x values and we divide or multiply x
I mean each value of x by a number, by a fixed value. For example, suppose here we multiplied each value by 2.5 for x. Also multiply y by the same value, 2.5. Y will be the same. In addition to that, if we multiply x by 2.5, for example, and y by 5, also r will not change.
But you have to be careful. We multiply each value of x by the same number, and each value of y by the same number. That number may be different from x. So I mean multiply x by 2.5 and y by -1 or +2 or whatever you have. But if it's negative, then we'll give negative answer. I mean, if y is positive, for example, and we multiply each value y by -1, that will give negative sign. But here I meant if we multiply this value by positive sign, +2 or +3, and let's see how can we do that by Excel. Now this is the data we have. I just make copy. I will multiply each value of x by 2.5. And I will do the same for y value. I will replace this data by the new one. For sure the calculations will, the computations here will change, but R stay the same. So here we multiplied each x by 2.5 and the same for y. The calculations here are different. We have different sum of x, sum of y, and so on, but are the same. Let's see if we multiply just x by 2.5 and y the same. So we multiplied x by 2.5 and we keep, it makes sense? Now let's see how outliers will affect the value of R. Let's say if we change 1 point in the data set, suppose I just changed 64. For example, if just by typo and you just enter 6, so it was 8.7, it becomes 0.7. So there is a big difference between 0.87 and 0.7, and just we change one value. Now suppose the other one is 0. 82. The other is 2, for example. 1. I just changed half of the data. Now R was 87, it becomes 59. So that means these values for sure are outliers, and they affect the correlation coefficient. Now let's see if we just change this one to be 200, it will go from 52 to up to 63. That means any changes in x or y values will change the y. But if we add or multiply all the values by a constant, R will stay the same. Any questions? That's the end of chapter 3. I will move quickly to the practice problems we have. And we posted the practice in the course website.